All right, so if you liked Asha Gabi's talk about merging biology and silicon, you're going to like our next talk. One of the alternative futures, they'll probably coexist, for AI hardware is neuromorphic chips. So these are chips that are silicon-based but entirely brain-inspired. And one of the companies right here in Silicon Valley that's working on a neuromorphic device is Rain Neuromorphics. So please welcome Gordon Wilson to tell you a little bit about that.
All righty, thank you so much. So my name is Gordon Wilson. I'm the CEO and co-founder of Rain Neuromorphics. And we build processors for artificial intelligence that are inspired by the brain. Our mission is to build the first hardware that can power brain-scale intelligence. And as you know, the title of my talk today is Building Bigger Brains. So I'm going to focus a lot on essentially what it will take for us to scale up our current hardware to get to brain-scale computing, to get it to much more massive artificial neural networks than what we currently have today. So a little bit about my company. There we go. A little bit about my company. We are a team of 14 right now, material scientists, data scientists, electrical engineers, CMOS engineers. We moved out to California a year ago to participate in Y Combinator. We were in the same class as a Fire CEO just before us. We have a few of our highlight of our investors. Notably, we're missing Rob, but Sam Altman, some other folks you may have heard of. And a little note I always like to say just for fun. We were founded on June 13th of 2017 in Gainesville, Florida. Our name is Rain, and June was the rainiest month on record in Gainesville. In any case, a few laughs maybe, but it seems like the weather seems to be following us as we're coming here to California. But in any case, what I'll really be talking about today, this will be split into 3 sections. The first is the current state of AI hardware. Like, who is winning and why are they winning? Like, what are the fundamentals underneath hardware that determine why NVIDIA is the current market leader? The second part, I'll talk about scaling. Basically, as we want to scale up to support larger, smarter artificial neural networks, what are the challenges that we'll face as we bring that up? And the last part, I'll be talking about our technology, one of the principles underlying it, which is this notion of sparsity, and also the emerging AI hardware landscape, because there are over 100 companies across the world that are building new silicon just to accelerate deep neural networks. So, part 1, AI hardware, who's winning and why? So, to first start at this, we should take a look at just the size of the AI hardware, the AI semiconductor market. So this looks at the current and moving forward into the future semiconductor market. And by 2025, we expect to have a $65 billion total addressable market just for AI silicon. It is growing at a far faster pace than the broader market for silicon. And according to this McKinsey report, there's a far greater value of the far greater proportion of the total value of AI that is to be derived from the silicon itself. They estimate for AI, it's about 40 to 50%. So it's very, very important. And who is currently winning? Well, we know that. This is the NVIDIA headquarters down in Silicon Valley. They've been doing very, very well for themselves, positioning themselves as the current leader in AI hardware. Their stock has done extraordinarily well. I think between the end of 2012 and most recently, it's gone from $15 to almost $150 trading. And if you buy something from NVIDIA today, it looks like this. This is an NVIDIA V100 GPU. And you're using it to run things that look like this. This is a deep neural network. But notably, NVIDIA was not always the deep learning company. They have not always been the AI company. In fact, I was actually an early customer of NVIDIA back when I was like 12, 13. So back in 2005, when I turned 14, this was the hottest graphics card on the market. And I remember begging my mom to take me to Best Buy so we could buy this processor so I could plug it into the PCIe slot in the back of my computer. I would unscrew the back, remove the cover, and plugged in that graphics card. And all of a sudden, when I turned on The Sims or Age of Empires, it was running so much faster. It was rendering the graphics faster and in far greater detail. So this is, again, a graphics processing unit. It was originally built to process graphics and render them. So here is ooh, it's a little pixelated. But this was Age of Empires, one of my favorite games. Nice. So between 2005 and 2019, the fundamental architecture of GPUs actually hasn't changed very much. But they are all doing the same thing. This is matrix multiplication. So if you remember back in maybe Algebra 2 and then later in calculus, you're first introduced to these matrices, which are just big grids of numbers that you multiply together. Now, why is this important? So when you look at matrix multiplication, you can represent a lot of different values in this big grid and then transform them based on some type of vector. Now, in graphics, each of these corresponds to like a pixel or a polygon, like a component of those images. In neural networks, this big matrix corresponds to the weights of the synapses, and the vector of activations is the actual information moving from the inputs through the network. So it was just basically on accident that NVIDIA ended up building the best matrix multiplication engine, and they could then become the market leader just like that. And a key note to remember as we go to section 2 is that the matrix multiplication in any processor is lots and lots of small calculations. You need to multiply this whole vector times this entire row and sum them all up together. It's lots of little individual calculations. That'll be important. All right, and NVIDIA really has this guy to thank, and we all really have this guy to thank. This is Jeff Hinton. He is one of the godfathers of artificial intelligence, of deep neural networks. He popularized backpropagation. And in 2012, he developed this architecture. And you probably heard in the last presentation, people talking about 2012 being a turning point. This was the turning point. And this is why. Because it was the first time that they actually used multiple GPUs to parallelize a deep neural network architecture. And they broke the benchmark by 11%. This was an incredible breakthrough, and this sparked this incredible renaissance that we've now seen over the last 7 years in deep learning. And it has only grown incredibly fast since then. This is a chart from OpenAI, and this shows the amount of compute that is required by the most advanced and best deep neural network models. See, they started with AlexNet back in 2012, and since then, we have seen a 300,000x increase in compute. That is immense. I don't need to say it's immense for it to be clear that it's immense, but it's doubling every 3.5 months. This is a breakneck pace of compute requirements. The models are becoming bigger and more complex. It's fundamentally driven by just bigger artificial neural networks with bigger matrix multiplications. And incrementally improving hardware, even if Moore's law wasn't slowing down, you couldn't take the same architecture and expect to keep up with this type of compute need. So, to summarize this first part, the AI hardware total addressable market is expected to reach about $65 billion by 2025. NVIDIA is the current leader because they have the best matrix multiply. And the compute needed for the most complex models is doubling every 3.5 months. So, part 2, the scaling challenges of digital simulations and analog hardware. So there are basically 2 ways to perform matrix multiplication. The one that we're all very familiar with is the GPU. So run it using digital hardware, digital components to perform this math with like standard digital logic, right? The second one, which you may have not heard of, but is actually gaining some popularity here in Silicon Valley, and is a resurgence from an old architecture, is analog. And that's using the physics of a system with resistances and voltages and reading out currents to perform matrix multiplication. And there are a number of companies that are commercializing just this for all those low-power edge AI applications. So we'll take a look at just what is kind of limiting each of these architectures from fundamentally scaling up so we can get to brain scale intelligence. Digital simulations simply scale poorly with time. As they get bigger, they take a long, long time to simulate. For 2 reasons: data movement and the von Neumann bottleneck, I'll explain what that means, and order n-squared scaling and matrix multiplication. I will also explain what that means. So when we say data movement and the von Neumann bottleneck, we're just referring to the fundamental architecture that all computers utilize, where you have a processing unit and a memory unit, and they're separated by a serial bus. Now, if you were going to do a matrix multiplication on a CPU like this, you would have to retrieve every unit that was in that value that's in that matrix, move it over to your processor, move it back and forth and back and forth. That would take a really, really, really long time. So GPUs look like this. They have lots of little processors that are distributed across their their hardware so they can parallelize this mathematics. And so they can save a massive amount of time and do a lot better. That said, even though these are the best of the existing hardware, 95% of the time that you run a deep neural network with a GPU, you're just moving data. And when we look at the total number of operations that are required to perform these matrix multiplies, this becomes a key limiting factor. As you increase the size of a layer in your neural network, the total number of operations to move data through increases as the square of that. So as you are getting wider computationally, it's an exponential curve that you're going up. So we see deep neural network architectures today that are very deep, but they're not very wide. So there's another way to perform matrix multiplication to run a deep neural network. There are companies like Analog Inference and Mythic and Sentient that are commercializing variations of this technology right now. And they have hardware that looks like this. You have physical neurons, if you will, along two edges of a chip. And then you have a grid of synapses that connects those two rows of neurons. These serve as your inputs and your outputs. You release a series of voltages from these input neurons into this mesh, into this grid, and there's a resistance value at each one of those cross points. So you can actually perform matrix multiplication with the laws of physics, with Ohm's law, in one step. So this not only saves you energy, but it is also much faster. So it's natural that there's been maybe $200 million in the last year from VC poured into these types of architectures. So this is a crossbar array. And the time scaling of this is also really, really good. You can avoid the poor time scaling of digital hardware with these analog devices. So this would imply that people would be using this architecture to scale up, but they're not. The problem is this scales poorly with space. As you increase the size of this chip, your neurons are increasing on the edges linearly, and the size of the chip is increasing as a square. So the density of neurons on your chip is decreasing as it increases in size. You can't fit enough neurons onto one of these chips. This won't scale up either due to space. So what people have tried to do, like at IBM, is they keep the crossbars small, they tile them across a board, they call it a network on chip, but you can't get big matrix multiplies, and now you have serial communication between each of those. So this begs the question and kind of comes back to our inspiration as a company. So we know that that theoretically we should be able to build a brain scale processor because there's an existence proof between our ears. Right? There's a massive artificial neural network that we have with 86 billion neurons and almost a quadrillion synapses. So how does our brain scale? It scales with sparse connections. If you think back to both the crossbar and that image of the simulation, they had fully connected layers. Every neuron in one layer was connected to every neuron in the next layer, and every neuron in that layer is connected to every neuron in the next layer. The brain doesn't do that. There are no fully connected layers in the brain, but they're sparsely connected. And they're connected in patterns that are incredibly, incredibly efficient. There's one pattern called a small world network topology, which is basically what it sounds like. It's like the same idea as with people in social networks, where we have 6 degrees of separation between us. So even though any given person has a small number of social connections, there's a short path to bridge from any person to any other person. The same is true of the brain. Even though of all the possible connections that could exist, a small subset exist, there's a short path length to bridge from any neuron to any other neuron. And therefore, you can move information incredibly efficiently through this special type of network. The brain also utilizes low precision analog physics, so much more similar to the crossbar, to compute information. And as we know, it scales to be immense. So, to summarize part 2, the scaling challenges. Digital simulations scale poorly with time. Existing analog hardware scales poorly with respect to speed, but the brain scales to a massive size with sparsity. All right, so part 3. We are inspired by the brain. We are neuromorphic, but we kind of run against the dogma of the neuromorphic engineering world in the past. Historically, neuromorphic engineers, and this has been around for like 30, 40 years, have been really focused on replicating exact neurons, like making sure a neuron looks just like the way a neuron would work in biology, like replicating the biochemical gradients or things like that. we think that's misguided. Like the important inspiration to draw from the brain is what emerges at scale. The mathematics that emerges when you have massive, massive neural networks that you can perform operations on. So when we look at the brain, we can observe these small world network patterns. And as it turns out, these are nanowires that were fabricated in our laboratory at the University of Florida. You can find the same type of small world topology emerging from a random mesh of nanowires. This is the key insight that led to our first patent 5 years ago at UF. So this means we can now build a new type of chip. We can utilize analog computation to perform matrix multiplication very quickly and very energy efficiently. But now we're no longer limited by the spatial scaling of the crossbar. We have, instead of neurons on the edges, we have neurons covering the entire chip. And we have a new interconnect layer of these random nanowires that are coated in a memristive material that connect the neurons together in a brain-like topology. This allows us to perform matrix multiplication through this mesh of nanowires and scale up that matrix multiply to 1,000 times larger than what would be practical in digital or analog hardware today. So it's sparse, low precision, and scalable. You have constant neuron density as the chip size increases, and you can fit up to 10 million neurons in a single square centimeter. So to emphasize the scaling comparison, digital simulations have order n squared scaling in time. Existing analog approaches, unfortunately, have order n squared scaling in space. And because we are eliminating synapses and replicating this sparse pattern that we observe in the brain, we have order n scaling in space and time. We want to build bigger neural networks. And our first product will be a PCIe card, so the same form factor as a GPU for both training and inference. Several of these chips, or these die, tiled across a board, and we're building it so it can be programmed with the existing tools that deep learning engineers already use today. We want to replace the largest fully connected layers in existing neural networks with even larger layers. We want people to build far, far larger artificial neural networks than what they're currently limited to today. And trust me, it's something that deep learning engineers are really frustrated with. They're stuck within this box of how wide they can build their networks, how much data, how many dimensions they can actually build into this model. And they want to build them bigger. And we have up to 700 times lower latency on the largest neural networks. So this is how we see the emerging market landscape. So we have two axes, the x-axis being complexity, i.e. the scale of neural network that's supported, the size of the architecture, and the y-axis is energy efficiency. So in the bottom left corner, this is like the existing hardware, the hardware that's on the market today. We have a CPU in the bottom left, not built for neural network processing, but we have a GPU in the top right. It is built for neural network processing. We see a lot of companies now emerging onto the market that are essentially taking, I say, variations on a theme of a GPU and re-architecting this so they can build the next generation data center appliance. Those are some of them. And then you have people that are building with either the analog hardware or digital signal processing low power devices. But in general, those don't scale. They're just taking the existing models, the existing types of intelligence that we've already proven, and moving them into smaller and more efficient form factors. And then, because we have analog computation and we can scale to large sizes, we want to target the markets where you need complexity and efficiency. So the markets such as robotics, autonomous vehicles, you can probably guess the rest. And of course, ultimately, as we're scaling up, our true inspiration and the thing that we're measuring ourselves against is the brain. 86 billion neurons, nearly a quadrillion synapses, with 20 watts of power running fully asynchronously in real time. It's a great benchmark to have and to compete against. And I'll leave you with this quote from one of our advisors who was a hardware guy at Nirvana before they were acquired by Intel and is now the lead hardware engineer, or hardware scout, I should say, at OpenAI. He said this about us. We're very excited about our work with OpenAI and their interest in how we want to build brain scale hardware. So that's all I have for you today. Thank you so much.
All right, any questions? If not, I'll ask the first one. So a lot of people who are not familiar with the hardware industry has a very different set of stages than the software industry, right? You don't sort of build an MVP and then do some pilots and whatever. Like, tell us a little bit about sort of what the commercialization process is like for technology like this and where are you in the process?
Yeah, absolutely. So it is much longer than software. With us, probably the first stage is you have a proof of concept, you have the idea, and you want to simulate that to benchmark your hardware in like some type of simulation. So we've run extensive simulations of various densities, various sizes of our technology. You have to build multiple kind of hardware proofs of concept on your way up. We already built a 50 neuron proof of concept. We're now taping out our first silicon in 3 weeks, which is a 10,000 neuron chip. So it'll be able to do a 5,000 by 5,000 matrix multiply. But the first product that we aim to bring to market will be a board that has between 6 and 8 die with 160,000 neurons. And we would like to have that ready in about 2.5 years.
Gotcha. I think we have another question.
What evidence do you have that sparse connectivity is going to work with the wide networks?
A lot. So it's a field that's been a kind of a field of interest that's been growing a lot in deep learning recently. And there's been recently a number of publications that are looking at specifically expanding the width of neural networks and doing so with sparsity. So Scott Gray, the guy whose quote I just read up there, he recently published, not recently, but published a blog post called Block Sparse GPU Kernels, where he was taking blocks out of the layers. And in that blog post, the really incredible insight that he had there was that kind of the obvious consequence of sparsity is that as you reduce the total number of computations, as there are a lot of zeros, it takes less time, it takes less energy. But what was really amazing was these sparse layers, these models with sparse layers that you could compare it to another model that would take the same amount of computational time, were performing with better accuracy than their alternatives. So not only is it reducing, there's something integral to sparsity that relates to the sparse structure of information that is going in the first place. So we're pretty certain that sparsity is the key to get there.
I have one more question.
Yes.
What do you think about similar efforts going on at a place like NVIDIA? Because there are smart engineers there, so if you think your architecture is going to work, it's pretty sure they are copying it, right?
Well, so NVIDIA is building GPUs, which are digital hardware fundamentally, and they are trying to scale with Moore's law. So, NVIDIA and all the players who are building digital hardware that are trying to track along the Moore's law curve are facing kind of all the same issues, that it costs a huge amount of money to tape out in 17 nanometers. The cost of making a mistake is massive, and there's past a point, the physics of that silicon just won't scale anymore. So, we think we need to fundamentally reimagine a processor to be able to kind of start a new scaling curve up. I didn't put up there, but we're building our first chip in 130 nanometer technology, which is a lot bigger than like 17 nanometer technology that the NVIDIA GPUs are building.
Do you think it's really hard for them to copy exactly what you're doing, say NVIDIA or anyone else?
Yeah, no, I mean, the core IP of our technology is around the materials. NVIDIA, to my knowledge, doesn't have a resistive memory team. And one of the challenges of kind of building with these types of stochastic materials is you have to integrate the algorithms with the materials through the architectures. So it's kind of an interesting thing we're trying to build with our company, and to have these feedback loops within our engineering teams, where in other conventional semiconductor spaces, they'd be siloed. So I think it would be pretty challenging, for a conventional company to do what we're doing.
Okay, let's hear it for Gordon. Big round of applause. Thank you, sir.